And just let me know if my voice drops because I'm traveling at the moment and the internet quality might not be that good. So anyways, we were doing rate of reaction, and I said that you measure any change with respect to time. So if that change is happening, that could be an increasing or decreasing change. So if you have any reaction, the change could be anything. You could measure anything with respect to time as long as it's changing as the reaction happens. So we did the magnesium plus hydrochloric acid reaction, and we can measure the volume of hydrogen gas. How much is that changing with respect to time? Or how much is the mass of the solution decreasing with respect to time? And I said that the steeper it is, the bigger the gradient, the faster is going to be the reaction. And then we moved on to the 5 factors, which were you had temperature, you had pressure, you had concentration, and you had surface area and catalyst. These were 5 factors that would affect the rate of a reaction. And we were only interested most in concentration at the moment because and we're going to figure out how the rate of the reaction varies when concentration changes. So the reaction is dependent on collisions of the particles. And we talked about the order of reaction. I gave you a brief overview of what the order of reaction is. And I told you that if you have a reaction and you've got X and Y reacting together, then the reaction depends on the concentration of X and the concentration of Y. Like if you have a higher concentration, there would be more collisions and the reaction would be faster. Vice versa, if there is less concentration of X and Y, then the reaction would be slow. So the rate of the reaction is proportional to the concentration of X and the concentration of Y. So if any one, so it's dependent on both of these. K is the constant, which is known as the rate constant. You add that so that you get rid of the proportionality sign. And remember, this K is a rate constant, and this K only changes with the, there's only one thing. I think I must have written it somewhere that maybe I didn't, but this K only changes with temperature. I'll just add this over here. That K increases with temperature. Like if you keep the concentration the same, the rate increases because the K value increases with temperature. But we're not that interested in K at the moment. So we can just keep that aside. So the last thing that we talked about was that rate is dependent on the concentration of X and the concentration of Y. And there's going to be some power A and B. That determines the relationship. That fine, rate is dependent on the concentration of X. But how exactly is it dependent on the concentration of X? Like if the concentration of X increases, what happens to the rate of the reaction? So if the order is kept as 1, that means rate is dependent on the concentration of X and the power is 1. That means it's directly proportional. Like if you change the concentration of X, the rate would increase proportionally. That means that if the concentration of X doubles, the rate of the reaction would also double. Then you had order 0, which meant that if rate is dependent on the concentration of X and the power is 0, that means that changing the concentration of X is not going to have any effect on the rate of the reaction. Like no matter what the concentration of X is, power 0 means that it's going to come out to be 1. So the rate value would not change if the concentration changes. So that means, what this means is that concentration has no effect on the rate of the reaction. And then we had order 2, which was that order 2 was, so order 2 is order 2 is rate is dependent on the concentration of X, but the power is 2. That means that if you change the concentration of X, rate is affected by a much greater amount, which means that order 2 means you double the concentration of X, the rate of the reaction would quadruple. If you increase the concentration of X 3 times, the rate of the reaction would increase 9 times. So it's a quadratic relationship. So you had these 3 orders that we know that rate depends on the concentration of X or any of the reactant. But how exactly is it dependent? Is the power 0? Is the power 1? Is the power 2? There could be power 3 and power 4 as well, but our syllabus is limited to order 2. Is this clear up till this point? Zoa, is this clear? Minahil, Alicia, is this clear? Nadine, all clear?
Yes, sir.
So we had started talking about graphs, like how do you identify order 0 or order 1 or order 2 by looking at the graph. How does the concentration, remember X over here is your reactant. So the first graph for order 0 looked like this. Remember, initially you have a lot of reactants. Like whenever you have a reaction, initially there's going to be a lot of X, and slowly over time the concentration of X would decrease because the reactants, they get used up. So the reactant would always go down to 0 eventually because they're going to get used up. So as the concentration of X is decreasing, the speed with which it's decreasing remains constant. That means you decrease the concentration of X, the rate of the reaction should slow down, but it doesn't slow down. Remember, the gradient is the rate of the reaction. So the gradient does not change. It should slow down. It should take longer time. Like normally this is what happens. Like if you're burning a match, even initially it burns very quickly and then it slows down and then it gradually dies off. So reactions tend to slow down, but order 0 means that the reaction is not going to slow down. As your reactants get used up, the speed with which it was decreasing initially, the same speed is going to be at the end. So it's just going to be one fast reaction. That's it. And the rate of the reaction is not going to change. So that is order 0. And then we're going to talk about order 1. Order 1 means that as your reactant gets used up, its concentration decreases. The rate of the reaction would also decrease. It would slow down. This is normally what happens. Like if you pour a piece of Pepsi in a glass, you'll see bubbles initially. There's going to be a very quick reaction, then the bubbles would slow down. So this is what you expect. Mostly it's directly proportional. Like concentration of X decreases, the rate of the reaction should also decrease proportionally. So how would an order 1 graph look like? It's going to look something like this. Like, so that's my X-axis, that's my Y-axis. Over here, I have the concentration of X plotted. And let's say it's 1, 2, 3, 4, 5, 6, 7, 8. So initially the concentration of X is over here. And this axis over here is time. So initially the reaction is very fast and the concentration of X decreases very rapidly. So it becomes half at this point. But then it slows down. And the gradient becomes less and less steep. So the reaction is slowing down as X gets used up. So the graph somewhat looks like this. So it kind of looks like this. Steeper gradient at the beginning, but then the reaction slows down. So initially steeper gradient. So that translates to a much faster reaction. And now at the end, the gradient becomes less steep. So now you have a slower reaction. So this is what directly proportional means, that as the reactant gets used up, the rate slows down. So eventually it's going to slow down and slow down. It's going to take a longer and longer time. So if I try to connect this further, I mean, we can go on further. So it's going to slow down. Is this clear? Order 1, the graph for order 1. Yes or no? Is this clear?
Yes, sir.
Is it going to touch the x-axis?
So let's do a thought experiment on that. Let's say, will it touch the TK, the x-axis? That means the concentration of x goes to 0, right? So imagine these two x and y reacting together. What would happen eventually? That the reaction would slow down. Why? Because the concentration of x is getting used up, right? And there's less and less. So the time is going on, and then you're left with, let's say, the very last particles, right? And let's assume that y is also decreasing. Now, imagine there are two molecules that are moving around in a very large volume of, like, you have a glass of water and there's just the last two molecules left. Then it's very highly unlikely that it will actually go to 0, because the last two molecules, and y is also decreasing side by side because y is the other reactant, so it's also decreasing. So eventually there would come a point where this particle and this particle would, I mean, they would take a very long time to meet. They wouldn't even be able to find each other in this solution. So in most reactions, the reaction never actually goes to completion, because the very last molecules, they're not able to find the other reactant with which they have to react. Is the point clear?
Yes, sir.
Okay, so it's I mean, theoretically speaking, it's never going to touch the x-axis. Just like the Coke, like the Pepsi glass that you poured in. Like even after 2 hours, there's going to be some bubble that's produced after after a very long time, because the last very few molecules, reactant molecules, they're finding the other reactant molecules because the concentration has decreased to such a small quantity that they're not able to collide with each other. So theoretically, the concentration is never going to go to 0, but it's going to come very close to 0. And this is what happens to most reactions. Most reactions, they never go to 100% completion, because the last molecules or the last particles, they have a very hard time finding each other. So now let's move to order 2. Now order 2 means that if I change the concentration of x, the rate has, I mean, it's a quadratic relationship. So if I double it, the concentration should, the rate of the reaction should quadruple, right? Or vice versa. If I halve the concentration of x, like if the concentration of x decreases by half, then the rate decreases, rate becomes 1/4. So either it speeds up by a much larger amount, you change the concentration of x, you increase the concentration of x, it speeds up by a much larger amount. Vice versa, you decrease the concentration of x, it decreases by a much larger amount. So that means that the time required for the reaction, it just keeps on increasing. It slows down too much in this case. So I'm going to make a similar graph now and explain what order 2 would look like. It's going to look, so let's say we have a similar graph, and this axis again is time, and this other axis is concentration of x. Now, and let's start at the 8th box. It's 1, 2, 3. 1 second. 4, 5, 6, 7, 8. Take this one. Let's start over here. So initially the reaction is pretty fast. So concentration of x decreases to half at this point. But then the reaction slows down too much, and the curve becomes less steep. And next time the reaction slows down, so this is 1 second, 1, 2, 3, 8, 9, 10, 11, 12. So it just keeps on slowing down by a much larger amount. So let's try and sketch this. Okay, I got this wrong. So that kind of makes sense. So the only difference is the reaction is slowing down by a much larger amount. It's taking a longer and longer time because it's an order 2 reaction. So the graph would kind of look like this. It would be fast in the beginning, but it would slow down. So it's going to take a much longer time to actually go to 0. So are the 3 graphs clear? All 3 of them. Yes or no? Is this clear? Nadine, is this clear?
Yes, sir.
Sam? Okay. So let's talk about these graphs. Like, how do you differentiate? Like, if you see these graphs, I mean, the first one is easy to figure out, like easy to spot. Like, whenever you see this graph, all you have to do is it's a straight line. So that's order 0, right? So if somebody sketches that one, that's order 0. There's a concept called a half-life. A half-life is the time that is required for the concentration to decrease by half. So that's a half-life. Second half-life is, I mean, it's the same half-life that you had in physics. So the concentration decreases by half. That is a half-life. The concentration then again decreases by half. That is your second half-life. The concentration then again decreases by half. That's your third half-life. So let's focus on this first, order 0. Although for order 0, you don't have to even learn the half-life because it's very clear from the shape of the graph. So the concentration decreases by half, the concentration decreases by another half, and the concentration then decreases by another half. So every time it's decreasing by half, and this is the time that is needed. Let's say this is the first half-life, T1. Then you have your second half-life. That's your time required for the second half-life. And this is your third half-life. That's the time required for the third half-life. So what's the relationship? The relationship is each half-life is half of the previous half-life. So each half-life is half the previous half-life. So each half-life is half the previous half-life. And this is something that you need to spot. What about order 1? In order 1, if you look at the graph, order 1 and order 2, the shape of the graph is almost the same, but the half-life is not. So in order 1, the half-life is constant. Like that's the time required for the concentration to decrease by half. The concentration to further decrease by half, it's the same half-life. The concentration time required for the concentration to decrease by the next half-life to become 1/8, it's the same half-life. So every time the half-lives are exactly the same. So T1 is equal to T2 is equal to T3. So whenever you have a graph and you have constant half-life, that is order 1. And the last one. In the last one, the reaction is slowing down too much. Like if you decrease the concentration by half, the rate becomes 1/4. So that's twice as much. So in this case, this is the first half-life. For the concentration to halve, the next time the half-life doubles. For the concentration to halve another time, it's the half-life becomes 3 times by it doubles again. So every time the half-life is doubling. So the first half-life And this is your third half-life. So each successive half-life is twice the previous half-life. Or we can simply say that each successive half-life doubles. Okay, so each successive half-life, it doubles. Is this clear? Yes or no? Is this clear?
Yes,
So,
sir.
Yes, sir.
so that's one thing, right? So now for this, you have to plot the concentration of X with respect to time. Now, and remember X over here is your reactant, right? Now you can plot this graph. You can plot this graph for any reactant, like if and you can measure its concentration. Now there's a question on how do you actually measure the concentration? That's an issue. As the reaction is proceeding, like if you have a magnesium plus hydrochloric acid reaction, so how do you do that in real time? That's an issue. So I'll just talk about some experimental issues now for making these graphs. Experimental. So this is more related to how you're going to do this in the lab. Now the first thing is most reactions have multiple reactants. So they've got multiple reactants. Now the point I'm trying to make is the concentration of X is decreasing and the rate of the reaction is also slowing down. But the whole issue is the rate decreasing because of concentration of X, or it's decreasing because some other reactant is also decreasing? Like over here, initially, what did we write? That rate was dependent on the concentration of X, but at the same time, it was also dependent on the concentration of Y as well. Now, maybe the rate is decreasing or not decreasing, or maybe the rate is affected by the other reactant, not by this X. But since the reaction is going on, but the speed of the reaction is being determined by this other reactant. So how do you ensure that? Because remember, it's if you want to plot, any graph like y is equal to x, if you want to plot a relationship between rate and x, what you have to do is you have to keep the other things constant. I mean, that applies to any equation. Like if you want to plot a graph, or if you want to find a relationship between rate and the concentration of X, how the concentration of X varies when the rate, and how does the rate change, then you have to keep all the other things constant. You have to keep Y constant. I mean, K is already a constant, so that's not an issue. But the concentration of the other reactant needs to be kept constant, because the concentration or the variation in the concentration of the other reactant would also affect rate. So remember this. I mean, this is an experimental thing that whenever you want to plot or investigate something, you have to keep all the other variables constant. That includes temperature, that includes everything, right? But the problem is most reactions have multiple reactants. So how do you keep these other reactants constant? Like, so I want to plot this relationship, but the rate is also dependent on this other thing, which is Y. And the problem is that as the reaction proceeds, the concentration of the other reactant will also decrease, right? Like if X is decreasing, then Y would also decrease. So now we have a problem. Like, how do I isolate this? how do I make a rate change with X only and keep Y constant? The way that is done is keep all other reactants in large excess. So keep all other reactants in large excess so that their concentration becomes almost constant. Okay, so that the concentration becomes constant. What I mean by that is, like you had your reactants, you had X and you had Y. So let's say this is, so you had X and you had Y. Let me add a few more X particles. And this X was reacting with Y. And the whole problem was that when X and Y were reacting, if X gets used up, its concentration decreases, then Y concentration would also decrease. Both of them would start to decrease. Now, what I mean by keeping Y in excess is that you add so much Y that even if a few molecules react and they get used up, then the concentration of Y almost remains unchanged. Like I'm going to add so much Y, and let's assume X and Y are reacting in 1:1. So if one molecule of X reacts, let's say one molecule is gone, its concentration decreases. One molecule of Y also reacts, but the concentration of Y almost remains constant. It doesn't change. By losing one molecule, by reacting one molecule of Y, its concentration almost remains unchanged, unaffected. Like if half of X react and the same amount of X also react, the concentration of X decreases by half, but the concentration of Y is still almost unchanged. If 100% of X react and and a few more molecules of similarly Y react, the concentration of Y still remains almost unaffected. So this is how you keep the other reactants constant. Like you don't want their concentration to affect the rate of reaction. You want their concentration to remain unchanged. So you add a lot of it, like keep all other reactants in large excess so that their concentration becomes constant. So your rate of reaction is only dependent on this other reactant. Like when it goes to 0, the rate of the reaction also goes to 0 because now there is no X. So Y will not be able to react. So Y is not going to affect the rate of the reaction. Is this point clear? Clear, Zoha, Sam, Nadine, Minahil, is this clear?
Clear, sir.
Okay, and remember this point that when you're trying to plot two variables, like rate versus X concentration, you have to keep every other variable constant. And Y is a variable. Y is going to get used up. But if you add too much of it, then even if it gets used up just a very tiny amount, its concentration pretty much almost remains constant. It doesn't change. So concentration of X would vary a lot. It would be 100%, then it would be 50%, then it would go to 20%. But at the same time, the concentration of Y almost remains unchanged. So that is one experimental consideration that you must do. Like when you're plotting this graph, when all these graphs were plotted, all the other reactants were kept constant. Their concentrations were kept constant by adding them in excess, large excess. And the second consideration is, how do you measure the concentration in real time? Now that's a tricky thing. Like how do you measure concentration of a reactant in real time? It says how to measure concentration in real time. One thing is, like if you have this reaction, magnesium plus HCl, and you're trying to plot this graph, like MgCl2 plus H2, right? And you're trying to investigate, how does the rate vary with respect to HCl concentration. And you want to figure out this X, you want to figure out the order. You look at the shape of the graph, like you'll measure the rate of the reaction or the concentration of HCl with respect to time. Okay, so that is what you're going to do. And the shape of the graph would give you the order. Like if it's order 0, that would be a straight line. If it's order 1, then you'll have a constant half-life. If it's order 2. So this is what you're going to plot. You're going to plot HCl concentration with respect to time. So how would you measure HCl? Remember, you have to do this in real time. Like as soon as you put Mg, HCl is getting used up. You have to do this in real time. So what you could do is you could either measure the pH, measure pH of the solution. I mean, a pH meter would give you real-time values. Like at 1 second, it will give you the H+1 concentration. At 2 seconds, at 3 seconds, at 4 seconds, and you'll be able to plot this kind of graph, like HCl concentration on one axis, time on the other axis. So that's one thing. Similarly, if it involves a base, you can do the same thing. You can measure the concentration. Similarly, if you have gases, if your reactant is a gas, so if a reactant is a gas, what you could do is the concentration is proportional to the pressure of the gas. So you can kind of measure pressure, like you can plot pressure versus time. You can measure pressure with respect to time. So as the gas gets used up, the pressure of the gas would decrease with respect to time. So you have a container and the gas is getting used up, and the pressure would also decrease. So it's going to give you something. It's going to have a similar shape. Either one of those, the three shapes, you're going to get that. And by looking at the shape, you'll be able to figure out whether it's order 1 or order 2 or order 0. And if things get way too complicated, like you can't measure the pH, you can't measure the pressure because the reaction is not a gas, you can do titration. You can perform multiple titration. Now that's a very difficult thing to do in real time. What you're going to do is, like, here's your, so perform multiple titration. What you're going to do is, here's your X and Y in solution. These are your two reactants. And let's assume that Y is added in a large excess. So here's your concentration of X. After, let's say, 5 seconds, the concentration of X decreases by half. So how do you measure that it decreases by half? You're going to take a small sample. So take a small sample. Remove a small sample and titrate it separately. Now, when you remove the sample, the reaction would still be going on. So the concentration of whatever X is would still be decreasing. So remove a small sample and put it in ice cold water. So reaction stops. And then perform titration. Like let's assume that there's HCl in it and HCl is getting used up. It's reacting with magnesium and it's getting used up. You immediately take at 5 seconds, you take a small sample out And when you take it out, you immediately put it in ice, so that, and you start titrating it with some base, and then you can measure the concentration or figure out the amount of HCl that's left. Then after the next 5 seconds, take out another sample and put it in ice, and then you perform titration. So reaction stops and titration can be performed. So these are some experimental considerations that you need to take into account. One thing is, when you plot a reactant with respect to time, you have multiple reactants. So you have to keep all the other reactants constant. So you will be able to figure out the relationship between these two. You don't want the other reactants to interfere. So you keep them in large excess so that their concentration remains unaffected. And it doesn't affect the rate of the reaction. And how do you measure the concentration in real time? I told you that you can measure the pH, whether if the reactant involves a base or an acid. You can measure the pressure of a gas if the reactant is a gas. If it gets used up, the pressure of the gas would also decrease. Or you can just continuously take the sample out and perform multiple titrations, and then measure the concentration with respect to time. So once you have that, and now modern labs have much better devices of measuring concentration, like they can measure concentration of specific particles that are your reactants. So it's not that you have to perform titration. This is specific to school laboratory. Modern labs, modern equipments have devices that can automatically, without even performing titrations, they can measure the concentration of a particular particle or reactant. And it can plot that with respect to time automatically. So is this clear? Any questions? All clear? Alicia, all clear? Minahil, Nadine?
Yes, sir.
You can just remember this thing that these three graphs, like if a reactant is plotted against time, what would order 0 look like? What would order 1 look like? And what would order 2 look like? This, you can clearly identify it's order 0. This, you check the half-life. If it's constant, then it's order 1. That means the reaction is proportionally decreasing. It's slowing down proportionally. And over here, the reaction is slowing down too much. That means it's order 2. So let's continue tomorrow then. Okay. So, okay, everyone. Take care. Allah Hafiz.